All right. So let us start looking at a few more important results, some important observations. Okay. I would like you to think about it and write down whether you think this observation is true or is false. Okay. So we are basically going to look at the use of the unit impulse and also the unit step. Okay. So the first one is u of n minus u of n minus 1. If you sketch it, is this equal to delta of n? True or false? Okay. U of n starting at n equal to 0, u of n minus 1 starting at 1, subtract the 2, you will get a one sample at n equal to 0. So, this happens to be true. Okay. Second question, if I want to take write down an expression for u of n, can I write it as a summation k equal to 0 through infinity delta of n minus k? Is this true or false? May be useful for us to expand it a little bit. Can I write it as delta of n plus delta of n minus 1 plus delta of n minus 2 and so on? Okay, can we write it like that? Answer is true, because delta of n has got a sample at n equal to 0 and 0 everywhere else. N minus 1 is shifted by 1 unit of time, n minus 2 is shifted by 2 units of time. So, this is also a true statement. Okay, number 3, statement number 3. Now, can we also say that u of n is equal to summation k equal to minus infinity to n delta of k? Okay, we'll have to think a little bit because it's not as straightforward. Okay, so what we are saying is, can we write this summation as delta of minus infinity? What is delta of minus infinity? 0 plus some large number of values, delta of minus 3, 0, delta of minus 2, 0, delta of minus 1, 0, plus delta of 0. So, when I go from minus infinity to some positive value, I will get, until you come n equal to minus 1, what you will see is that the summation is only going to give you 0. Okay. When you reach u of 0, that means your summation now has come to includes delta of 0. That means you will start getting 1. Okay. So, then anything beyond that, delta of 1. So, this is 0, 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 this is equal to 1. So, if I am doing my summation all the way from this side, I'll keep getting 0. I'm adding only zeros up until I reach this point. Now, once I go past that point, again I'm getting only zeros, but I already have one sample which is equal to 1. So, this will be equal to u of n. This summation will be equal to u of n, and therefore, this statement also is true. This statement is true. So, you should always write down an expression, because looking at it, it may not seem obvious, but once you write it down, it will be you will be able to then make a reasonable assessment. So, this is a true statement. Okay, we will look at a couple of more. Again, these are important for us to use it as a mechanism for practice. Number 4, summation of n equal to minus infinity to infinity delta of n. What is that equal to? Okay. So, it's actually we are using, if you look at the expression that we have written in the previous line, you will probably get an answer. But maybe let me just write it down just for the benefit. So, let us write it down as summation n equal to minus infinity to minus 1 delta of n. Okay, I'm splitting the summation into 3 parts. The first one goes from minus infinity to minus 1. Then we have delta of 0. That's the sample where n equal to 0. Then you have the summation n equal to 1 through infinity delta of n. Okay, by substituting these values of n, you can show that all of the values in this are equal to 0. Everything here is equal to 0. This is equal to 1. So, when I do a summation from minus infinity to infinity delta of n, this is equal to 1 always. Okay. And so, if somebody were to tell you this is equal to 0, it would be false. If they say equal to 1, that it is a true statement. Okay. The last of the exercises here, again you should be very careful. You write down the expressions, then you will be absolutely sure what we are. So, n equal to minus infinity to infinity. Okay. This is not the expression that we wrote down in the class, in the session last time. This is a different expression. This is x of n delta of n minus k. Okay. So, write down the samples that you get. The point at n equal to 0, you will get x of 0 times delta of n. Okay. The previous sample, x of minus 1 delta of n plus 1. Okay. Delta of n plus 1. Okay. You look at these samples, then there is a x of k, some one of the values, that will give you delta of 0. Then you have x of k plus 1, the next sample, this will give you delta of 1 and so on. Okay. Look at this, all these expressions, this is equal to 0. Why? Because delta of n plus 1 is 0, this is equal to 0. The only one that is non-zero is this one. This will be equal to x of k, because delta of 0 is equal to 1. This is equal to 0, and then so when you do this summation, what you will get is the sample x of k. Only one non-zero sample will be left, and that will be equal to k. Okay. Now, you may want to go back and look at the expression that we wrote down. That is a little bit different from the expression that we wrote writing here. Just for your reference, what we wrote there were x of n equal to summation k equal to minus infinity to infinity, k equal to minus infinity to infinity, x of k is the scale factor, delta of n minus k. So, basically this non-zero sample is occurring at n equal to k, and so this is what we wrote down previously. Okay, this is true, this statement is correct, this is a true statement. This is a true statement as well, but don't get confused between the two. They are different because the way they what is inside the summation is different. So, basically you just need to understand how to interpret that the variable there. Okay, so let us move on. I think this is a interesting discussion that we have had. We'll try to see if we can use these results in many interesting ways. So, to make this an interesting discussion, I will define a new signal called a unit ramp. Okay, it's a very interesting type of signal. This is a signal which I'll sketch it for you. It starts at time n equal to 0. It has got value equal to 0, 0 on all negative points. Then for n equal to 1, it has got a sample value equal to 1, n equal to 2 has got 2, 3, 4 and so on. This is what a ramp function is. Basically, it's like a staircase, it is going up. So, this ramp function r of n is defined as n times u of n. Okay, and we can say that this is equal to n for n greater than or equal to 0, equal to 0 for n less than 0. it's because it's multiplied by u of n, it is 0 for all negative values of n, and for all positive values of n, it increases as n increases. So this is the function r of n, it increases as n goes up. Okay. So what I would like you to do is to show that. Show that means you justify the following statements. I would like you to show first r of n, the ramp function, can be given as a summation, k equal to 0 through infinity, k times delta of n minus k. Okay, very straightforward. This is like writing down the ramp function using delta functions. Basically, this is the expression. So I'm sure that one is fairly straightforward for you to show. Second one, show that r of n can also be written as summation k equal to minus infinity to n minus 1 u of k. U of k, unit step function, you integrate from minus infinity onwards and show that this comes out to be the correct value. The third one that I want you to show, that the ramp function can be written as a sum of shifted unit step functions, starting with m equal to 1 going all the way through infinity u of n minus m. Notice that each of these, you start with u of n minus 1, then u of n minus 2, and then keep adding all of them, you will find that you get the unit ramp function. So again, this is just as an exercise for you to try out and make sure that you are comfortable with the expressions that we have derived. All right. Now, let us move on to another important aspect of the sequences that we have and build on the our understanding of the sequences. So, if you have a sequence, we can derive certain additional properties and certain characteristics from the sequences, and this is very useful for us to have. Okay, so if you have a discrete time sequence, let us say that you call that as a sequence x of n. If x of n is equal to x of minus n, that means x of 1 is same as x of minus 1, x of 2 is the same as minus 2. So basically there is a symmetry. Okay, we call this as a even sequence. There is symmetry in the sequence. Now, by the same token, if x of n has got symmetry, but it has got with a negative sign, this is called a odd sequence. Okay, sequence with a negative sign. So, even and odd sequences are very, very important for us. The reason they are important for us is because every sequence, any sequence, x of n can be written as a sum of two sequences. One is an even part and an odd part. Now you may say, well, how can that be? It's not, I mean, x of n may not be symmetric, but how are you saying that it can be made symmetric? Notice that you can obtain the even part of x of n using this simple expression. X of n is equal to 1/2 of x of n plus x of minus n. Okay, and similarly, if you can define the odd component as 1/2 of x of n minus x of minus n. Okay, if you define these two, add them together, you will see that what you get is 1/2 of x of n plus 1/2 of x of n, which will be x of n. So, any real sequence. So, this is for real valued sequences. Real valued sequences, a sequence may satisfy even property or odd property. Even if it does not satisfy the property, you can obtain an even part and an odd part, and which will satisfy the respective properties. Now, by the same token, if you are dealing with complex valued signals, there is a corresponding relationship. Complex valued signals or sequences, let us use the same term, complex valued sequences. And this is a case where we don't say even and odd, we call it as conjugate symmetric and conjugate antisymmetric. So, if x of n is equal to x conjugate of minus n. Okay. In this case, we say that this sequence is conjugate symmetric. Conjugate symmetric. Okay. And we can also say that if x of n is equal to minus x conjugate of minus n, then it is said to be conjugate antisymmetric. Conjugate antisymmetric. Okay. And using these relationships, you can come up with a expression for conjugate symmetric of n as 1/2 of x of n plus x conjugate of minus n. You can come up an expression for conjugate antisymmetric part, which is conjugate conjugate antisymmetric part CA, which is 1/2 of x of n minus x conjugate of minus n. And you can show that all sequences, complex sequences, can be written as a combination of a conjugate symmetric part plus a conjugate antisymmetric part. Okay. Again, these properties will become useful when you want to study these signals. And again, once again, let me remind us that if we are talking about periodic signals, we can't talked about it in the context of sinusoids, but it can be talked about it in the context of even non-sinusoidal functions. A periodic signal is one which satisfies the following property that if x of n is equal to x of n plus n for all values of n. Okay. And we also note that you can also satisfy with x of n will be equal to x of n plus 2n, right? Because if it satisfies for n, you can write it for x of 2n. Similarly, 3n, 4n, and so on. So the period of a periodic sequence is the smallest value of the integer that satisfies the relationship which is given by 1. Okay, the period of a periodic sequence is the smallest integer that satisfies equation 1, satisfying equation 1. Okay, I hope you are comfortable with that, because that then says if I take any multiple of the period, it will be periodic, right? So just like if you look at a sinusoid, if you look at more than one period, it will still be periodic. So, but the period is exactly equal to the minimum value at which you can satisfy this condition. I hope you are comfortable with that, and we are able to now move on to another important operation of the on sequences that we perform. Okay, again, a very important step. You must make sure that you take time, understand what is given in the lecture, go back and look at what is given in the textbook, and then look at the examples that we are going to be discussing with you today.